Eccoci, benvenuti. Welcome to everyone. This webinar will be in English, but my brief introduction will be in Italian. Non-Italian friends. Eccoci, benvenuti. Moment, technical problem. This webinar will be in English. Sorry for this inconvenience. Non-Italian friends will be able to follow the note in English in the slide. So now I continue in Italian for Italian friends. Benvenuti a questo appuntamento, appuntamento per me così importante, dedicato ad una delle figure più mistiche del mondo dell'audio professionale del Novecento. Parliamo infatti, come avevo preannunciato, di Richard Heyser e la sua creatura, la Time Delay Spectrometry. Definirei Heyser il Tesla dell'industria dell'audio. Altri webinar oltre a questo seguiranno con altri ospiti italiani e internazionali. Parleremo di Heyser con il nostro ospite, di cui sono veramente onorato avere la sua presenza, il professor Doug Jones. Welcome, Doug.
Yes, hi, thank you. Thank you very much. It's good to be here.
Thanks to be here. We have also a surprise, another special guest. We have with us Tom Danley. Welcome, Tom. Tom, can you listen me? Tom ci raggiungerà tra qualche minuto nel corso del webinar, perché vi ripeto è stato una sorpresa veramente inaspettata per tutti noi. Dopo questa mia breve introduzione in italiano con note in inglese nelle slide, il webinar sarà moderato in inglese dall'amico Abe Scheele dall'Irlanda. Welcome, Abe.
Hi.
Un amico insomma di vecchio corso ormai del lato oscuro della fase. Parafrasando una nota frase di Bernardo di Chartres, oggi viviamo sulle spalle dei giganti del passato. Ed il periodo a cavallo tra fine Ottocento e inizi del Novecento è stato caratterizzato da giganti che hanno gettato le fondamenta dell'attuale conoscenza nel campo dell'audio, dell'acustica, del sound reinforcement. Questi giganti erano matematici, acustici, ingegneri, oserei dire, veri e propri pionieri ed esploratori. Ne vedrete solo alcuni rappresentati qui, ma veramente potrei citarne tantissimi. Alcuni dei più giovani tra loro all'epoca sono oggi ancora vivi tra noi. Tra questi giganti un posto speciale è riservato a Richard Heyser per aver gettato le fondamenta dell'attuale conoscenza nel mondo delle misure dell'audio professionale, con la sua visione multidimensionale del fenomeno sonoro, visione multidimensionale ancora oggi non del tutto esplorata nel suo profondo. I contributi di Heyser nel mondo dell'audio includono l'invenzione della Time Delay Spectrometry, della trasformata che prende il suo nome, la trasformata di Heyser appunto, la spirale di Heyser, il TEF Analyzer con il contributo di altri scienziati, matematici, fisici, ingegneri dell'epoca e dalle aziende che intorno a questo progetto hanno lavorato. Come vedremo il TEF, infatti, ovvero l'apparato analyzer hardware e software basato sulla Time Delay Spectrometry, la fisica inventata da Richard Heyser, fu un progetto complesso elaborato nel tempo. Heyser e altri dei giganti di cui parliamo hanno instancabilmente calpestato il suolo di Europa e degli Stati Uniti, in particolare il terreno della fattoria dei Davis, Don e Caroline Davis. La loro fattoria infatti per molti decenni è stata terreno fertile veramente della formazione di eccellenza nell'audio professionale, prima che passassero il testimone di Sinaudicon, questa era la scuola che Don e Caroline avevano fondato, a Pat e Brenda Brown, attuale presidente e moglie di Pat. Qui Heyser ha potuto esprimere pienamente se stesso in piena libertà, formando insieme a Don Davis e altri giganti dell'epoca. Ne cito solo alcuni a titolo di esempio: Peutz, Patronis, Don Chele, intere generazioni di professionisti. Moltissimi workshop specialistici sulla Time Delay Spectrometry e sugli analizzatori su questa basati vennero tenuti negli anni praticamente fino alla sua prematura scomparsa nel 1987. Possiamo dividere la storia del TEF Analyzer in alcuni periodi principali, poi magari Doug Jones potrà essere più preciso di me. Nella prima decade, dal 1967 al 1977, sono solo due persone, due utenti che sono in grado di spiegare la Time Delay Spectrometry. Il suo inventore, Richard Heyser, che la può spiegare nella sua interezza, e Cecil Cable, che aiuta Heyser nella realizzazione dei primi sistemi hardware in grado di applicarla e nel strutturare anche il suo insegnamento con il supporto dei Davis. Infatti Don e Caroline Davis nel maggio del 1977 iniziarono ad ospitare in maniera costante sia Heyser che Cecil Cable, insegnando la Time Delay Spectrometry in maniera organica e strutturata all'interno dei corsi Synaptic. Cecil e Barbara Cable divennero amici di viaggio dei tour formativi dei Davis in lungo e in largo per gli Stati Uniti. In un primo documento destinato ai partecipanti ai corsi, Don Davis così spiega i principi basilari della Time Delay Spectrometry. Siamo nel 1977, nel giugno del 1977. Ecco, lascio qui nella registrazione, in modo che possiate consultarlo con calma, il documento che spiega i principi basilari della Time Delay Spectrometry, scritto da Don Davis stesso, non essendoci ora il tempo ovviamente di addentrarci. Nel periodo dal 1977 al 1979 si sviluppa la formazione Time Delay Spectrometry come un'unica licenza TEF che comprende la fusione delle licenze e formazioni specifiche della Time Delay Spectrometry e della Energy Time Curve, una formazione dunque più globale per l'analisi del tempo, dell'energia e della frequenza. Si inizia ad assemblare nel garage di Heyser letteralmente, e durante i corsi stessi i primi prototipi del TEF. Synaptic diventa l'unico ente di formazione e rilascio delle licenze. In questo periodo tanti giganti si avvicinarono e collaborarono con Heyser. Cito solo a titolo di esempio Patronis, Peutz, ma veramente furono tanti. Il primo workshop TEF, denominato The 20, comprendeva 20 professionisti da tutto il mondo che, intuendo insieme a Don Davis la portata delle teorie del lavoro di Heyser, decisero di investire il loro tempo e anche le loro risorse direttamente nella definizione di quello che fu il prototipo di quell'analizzatore basato su TDS, che poi successivamente verrà sviluppato in maniera più organica, il TEF. Nel periodo tra il 1979 e il 1982 il TEF viene ingegnerizzato come unico apparecchio hardware e software per la sua produzione su larga scala. Per Heyser e Don Davis la scelta dell'azienda cui proporre questo progetto era fondamentalmente semplice. Occorreva un'azienda che avesse le menti capaci di comprendere la matematica e la fisica TDS e di impacchettarla in un unico strumento hardware e software, dicevamo, efficiente e avanzato. Fu scelta Crown, che in realtà già dal 1960 iniziò ad interessarsi delle cose di Heyser. Gli ingegneri che si occuparono di questo progetto furono Gerald Stanley e Don Eger. Ecco una testimonianza di Don Eger su Heyser. Heyser mi ha detto che la Time Delay Spectrometry è come spalmare il pane tostato con il burro e poi raschiare il burro e guardare alle briciole. Diceva Heyser che alla natura non importa come la guardiamo, in poche parole, dobbiamo solo trovare il modo migliore per guardarla, in modo da non dover essere vincolati a costanti di correzioni come la costante di Boltzmann, per esempio, ed altre. Ecco alcuni dei nomi che per primi lavorarono al progetto TEF e il loro specifico campo di applicazione. Gerald Stanley, ovviamente, Donegger, Patronis, Peutz con il professor Bangkok, che si occuparono del pacchetto software legato alla intellegibilità, no? Don Chele, che sviluppò i programmi di analisi per lo STI e per il Rasti, ed altri che non stiamo qui a citare, ci saranno altre occasioni per farlo. Seguirono anni di sviluppo e diffusione, ovviamente, del TEF, gli anni d'oro, fino alla prematura morte di Richard Heyser, avvenuta nel 1997. Nell'ottobre del 1978, questa è una testimonianza a cui tengo tanto perché è del nostro caro amico Ray Barn, recentemente scomparso. Diceva Ray, no? Nell'ottobre del 1978 ho ottenuto una licenza da Caltech per utilizzare e insegnare il brevetto TDS di Heyser. Da allora ho osservato i sistemi audio nel dominio del tempo. Una volta che inizi a fare misurazioni consapevoli nel dominio del tempo, non vorrai più tornare indietro, diceva Reino, nell'uso di sistemi time blind. Oggi ci sono molti sistemi, tra cui System, che possono effettuare misure consapevoli nel dominio del tempo. Questa è una riflessione di Reino di qualche anno fa. Ora sicuramente Heyser si trova in compagnia di giganti come Archimede, Newton, Leibniz, Laplace, Fourier, Hilbert. La trasformata di Heyser è un fatto storico, in definitiva, che non può essere ignorato o minimizzato, eppure oggi il mercato l'ha un po' oscurata. Potrebbe volerci del tempo, un altro secolo probabilmente, prima che la sua piena importanza venga realizzata e compresa. Bene, termina qui la mia brevissima introduzione, lascio immediatamente spazio agli ospiti perché avranno tante cose evidentemente da dirci, da regalarci. Abe, we are ready for the presentation.
Okay. Allow me to introduce Doug. Doug Jones is Professor of Acoustics Emeritus and the founder of the Audio Arts and Acoustics Department at Columbia College, Chicago. He has worked in acoustics on 6 continents on projects ranging from radio stations in developing countries to internationally recognized recording studios. At Columbia College, he was the first to offer a college course on time delay spectrometry. He was also instrumental in acquiring Dick Heyser's lab equipment and his papers. These are now housed at the archives at Columbia College, Chicago. In 2006, he was awarded the Richard Heyser Award for his contribution to electroacoustical measurement. Doug is the author of Sound of Worship, Taylor and Francis 2010, a book that examines the relationship between theology and acoustics of worship spaces. In addition, Doug is contributing author to the prestigious Handbook of Sound Engineers on Vocal Press. Doug's contributions have appeared in the 3rd, 4th, and 5th editions. In the 5th edition, he authored chapters on small room acoustics, noise control, magnetic recording, loudspeaker theory, co-authored with Tom Danley, who we have here today, thankfully, and acoustics of worship spaces. He is also a studio musician, an engineer, a producer with numerous album credits. He performs regularly with a number of bands in the Chicago area, including frequent gigs playing Irish folk music. Doug is Thank you. Doug is currently employed at Sound Specialty Company, where he is Senior Design Engineer. Doug is a member of the Audio Engineering Society and the Acoustical Society of America. And from my experience, if you get a chance to talk to Doug sometime, you will learn a lot and enjoy every minute. Thanks for coming, Doug.
Okay, well, thank you for that kind introduction. Today I'm going to try something that is extremely difficult. I'm going to try to introduce you to not only Dick Heyser, but time delay spectrometry in, well, a little bit more than 40 minutes. And I'm not sure that's possible, but we're gonna give it a try. Let me see how I can share a screen. Hold on just a second. Let's see if we can get this working. Okay, is that looking right, Abe?
I don't see it yet. If you, there it is. Perfect.
Okay. So you're seeing the correct screen, right?
Yes.
Okay, good. Just checking. Okay, so first, let's just go over some of the terms that we're going to be using in this presentation, just so that we're all on the same page. As you can see on the screen, TDS stands for time delay spectrometry, which was the measurement approach invented by Dick Heyser. TEF is the name of the purpose-built analyzer that utilizes time delay spectrometry. ETC stands for energy time curve, which is a TDS measurement showing energy as a function of time. The EFC, which we more commonly call the frequency response curve, and the FTC, which is an unusual display of frequency versus time. Okay, so Dick Heyser, wow. You know, some basic facts. Born in the 1930s in Chicago, got his BSEE from University of Arizona, got his MSEE from Caltech, and went on to do some postgraduate work at Caltech, heading towards a doctorate, which he never completed. It appears that in 1956, he was sort of conscripted into Jet Propulsion Lab, which is a division of Caltech. He became a research scientist working on early satellite and imaging system. Now, fortunately for us, audio was his hobby and his passion. He loved listening to music. And he would often wonder why it was that he could hear stuff, but he couldn't measure it. And he says at one point he decided to try to take this on because he couldn't afford the $50,000 or even more than that to build an anechoic chamber just for his hobby. So we wondered, is there a way that I could build, using my mathematic background and my science background, could I build an instrument that would allow me to make anechoic measurements in my living room and begin to find out why it is that what it is about the speakers that makes them sound the way they do. He was passionate about the subjective part of the audio experience. He used to say that audio is n-dimensional. We don't know how many dimensions it has. We measure what we measure because we know how to, right? So when he invented time delay spectrometry, he realized that he had a tiger by the tail. That's his words. He realized that time delay spectrometry unveiled a whole new paradigm. And a paradigm is something that's very fundamental. It's kind of like one of the paradigms that happened a number of years ago was, instead of the understanding that the sun moved around the earth, the new paradigm was that the earth orbited the sun. Now, obviously, in that instance, that caused a lot of stir, and a lot of the scientists of the day and theologians of the day certainly said, how could that possibly be? And of course, from an observation point, it's hard to tell the difference, but nonetheless, this was a new paradigm. And Heyser believed that he had stumbled upon a whole new way of looking at things. That TDS was not just simply a tool for making measurements. It opened up a whole new understanding of energy, of time, of place, of space. And his ideas actually conflicted with some notable scientists like Einstein, Bohr, Heisenberg, Rayleigh, and others. And in the papers that we find in the archives, we find areas where he actually took them to task, if you can believe that. And of course, his radical views made him the target of a fair amount of criticism in his day. So the very first time delay spectrometry system dated back into the late 1960s. The system cost around, as you can see here, $40,000, probably more than that, in 1970 dollars. And this is a slide, again, from the archives drawn by Heyser in his own hand. So this is kind of special to see. This is the hookup. You had an HP spectrum analyzer, an offset oscillator, an FFT box, and then an FFT. And down in the bottom part of the page, you see the actual circuit of what was inside that FFT box. It's just a transistor, some caps, resistors. And the cool thing is it's powered by the signal. It doesn't require batteries or power supply. And I think that's typical Heyser. Now, Caltech owned the patent to time delay spectrometry. So you actually could not do TDS or build a time delay spectrometer, an instrument to do it, without a license from Caltech. And I think Fideli may have referred to the 20. The first people to actually get training on this new system and get a license to actually perform time delay spectrometry, they're known as the 20, and the cost, I think, of the seminar included the license to build a TDS unit for their personal use. The first commercial license was issued to Crown. They built the TEF-10 in 79-80. The TEF-12, which is shown here, was released a few years later in 85. Very similar machines. The cost of the TEF-10 originally was $15,000. A few people are aware that there was actually another company that was licensed to build a purpose-built unit. Brüel & Kjær was issued a license right about the same time. Their system was released in 81, I believe. And this is the control unit for doing TDS. You can see all the familiar controls if you're familiar with time delay spectrometry. And here's what the whole system looked like. Now, I certainly don't know anyone who ever bought this. I can't imagine anyone putting that much Brüel & Kjær together, certainly not mere mortals like us. So, cost is unknown, but suffices to say, it was probably quite expensive. Okay, moving on. The TEF-20 was introduced by Crown, and it was the first TEF that used the host computer to run the software. The first TEF was its own microprocessor built in. It was, for those of you who are computer geeks, it was 3 Z80s running at a maximum clock speed for them, and I forget what that was, but this is, this was a big deal for the time it was created, and it ran on DOS. Okay, so this is the TEF-20, about $4,200, and it was a big step forward, I think, from the TEF-10. Although there's some things that the old TEF machines could do that none of the modern ones can, but maybe we'll talk about that later. And then finally, in 1998, Goldline acquired the TEF Products Group from Crown International. And for a number of years, they built the TEF-20. put a different color paint on it, changed a little bit of the circuitry inside, but essentially it was the same TEF-20 that Crown built. And then in 2005, they released the TEF-25. The cost was $1,500. Now, I checked with Greg Miller, who is the owner of Goldline, and he assures me that the TEF-25 is still available. I thought they had gone out of business, but they haven't. So this is his email address. You can write him an email, ask him for more information. He'll be glad to talk with you if you're interested in buying the TEF-25. He told me that General Motors measures all of the cars on his production line using the TEF-25. So they're using time delay spectrometry to measure every car that comes off the production line. So he still sells them to General Motors. So it's still a box that's available. Okay. Now I'm going to start another section of this presentation. And we're going to talk a little bit about how time delay spectrometry works. And this is aimed at people who have never heard of TDS, who don't understand how it works. This is my attempt at giving you some idea of how this came to be. And part of what I'm going to say is, for those of you who may be students of time delay spectrometry and understand it more fully, you're going to recognize that some of the things I say you could take exception to. And that's what happens when you try to simplify things too much sometimes. You wind up glossing over some pretty profound things. So we'll probably do that. So forgive me. But let's just take a look at this. Now, remember, what Dick tried to do was build a device where he could take anechoic measurements. That means anechoic chamber is a room that is not only completely devoid of reflections, but it's also very, very quiet. It has usually an anechoic chamber will have noise floor down around NC10. So these are rooms that have no extraneous noise, and whatever sound that is made in that room is 100% absorbed by the walls, the ceiling, and the floor. And if you've ever been in an anechoic chamber, you know it's a sensory deprivation. It's a scary place to be. And if you do go in there, don't let anybody turn the lights off. It's really scary then. Okay, I digress. So imagine a room with a loudspeaker, a microphone, and let's say they're 10 meters apart. And of course, there's sound that goes directly from the loudspeaker to the microphone. There's sound that bounces off the ceiling and arrives at some time later, right? Because it takes longer to bounce off the ceiling. And there's a reflection off the floor that arrives sometime later. There's also things like noise in the room, right? There's the typical noises that you're going to find in anybody's home: the refrigerator, the air conditioning system, who knows? And of course, there's noise on the outside of the room. There's emergency vehicles and airplanes and whatnot. So what could we do to figure out how to get just the direct sound and ignore everything else? Okay. So if we connected a sweeping sine generator to the speaker and, played a tone or a sweep, let's say from 100 hertz to 15K or whatever. And we simply measured that at the microphone, what would we see? Well, we would see everything. We would see the sweeping sine wave. We'd see the noise. We'd see the reflections and everything. So how could we improve on this? Well, Heyser's brilliant idea was to put a tracking filter on the output of the microphone. And this is what the tracking filter looks like. And you can see that if the direct sound arrives sort of in the middle of the filter, that the reflections are going to be attenuated by the sides of the filter. And this is what the filter really looks like in real life. But for this conversation, I'm just going to use this symbol to represent the tracking or sweeping filter. So let's put that up here. And we're going to say that we're going to sync that sweeping filter to the sweeping sine generator. So this line that goes, I don't know if you can see my mouse. Mouse isn't working. I don't know if you can see this line here. This is the sync connection. Okay. And we've got, we can adjust the sweep rate. We can adjust the sweep range. So the sweep rate is how fast does it sweep across this range? How fast does it get from 100 hertz to 15K, for example? And of course, that will be synced with the sweeping filter. And the sweeping filter, we have two controls. We can control the delay of it, and we can control the bandwidth. And the delay means that we can control when it starts to sweep relative to when the generator starts to sweep. So, congratulations, we've just invented time delay spectrometry. But let's go a little deeper. We saw earlier that the distance between the loudspeaker and the microphone was 10 meters. Now, imagine that we have that sweep from 100 hertz to 15,000 hertz. If we delay the start of the sweeping filter to the time of flight of 10 meters, which is about 34 milliseconds. So it takes 34 milliseconds to leave here, pack a sack lunch, travel along. 34 milliseconds is a long time, right? And finally gets to here. If we put that figure in this delay control, then the filter will be, if you will, waiting for that first sound to arrive, that 100 hertz sine wave. And it will leave the speaker and arrive at the microphone just as the filter is looking for it, if you will. And as long as the sync generator and the sweeping filter stay in sync, as each successive frequency arrives at the filter will be in the right place to let it in. Nothing else will get in. The reflections will all arrive too late. And what's more is that the only noise that will get into the system is that noise that is present at that exact moment, at that exact frequency that the filter is tuned to. That's pretty cool. So let's say that the first reflection of the ceiling arrives at 40 milliseconds. Well, if we were to set this delay to 40 milliseconds, then we could look at what is the response of the signal bouncing off the ceiling. And we might, compare that to the sound that arrives at the direct sound. And we could do some fancy mathematics and subtract one from the other and actually see the absorption characteristics or what is lost in the ceiling bounce. And if we broaden up our bandwidth a little bit, we could say, well, I want to see the direct sound plus the ceiling bounce. That could be cool. But one thing starts to become evident here, at least I hope it does, that if we were to make the bandwidth of this filter very large, it would be like having no filter at all. We would see everything, right? We'd see all the reflections, we would see all the noise, everything. But if we did that, what we'd wind up with is a system that would have maximum resolution in the frequency domain. In other words, we would know a lot about the frequency domain, but we would have no resolution. We would know nothing about the time domain. And that may be a little difficult to wrap your head around, but I'll say it again. If we make that filter very large, we lose resolution in frequency. We lose resolution in time. See, I'm confusing myself. And we gain it in frequency. Conversely, if we make that filter very, 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 very small, we would know precisely when the signal arrived. But because the filter is so narrow, we would lose resolution in frequency. This is always going to be a trade-off. This is always going to be a trade-off. Let me talk about resolution just for a moment. What do I mean by that? Well, resolution is the ability to resolve detail. And you might say, well, okay, what should my resolution be? Well, it sort of depends on what you're trying to do. And an analogy I like to use is, imagine you were in the printing trade. And your job in that printing trade was to look at the fine, you were a font designer. And you want to look at each individual letter, and you might use a magnifying glass to get right down there and zoom in on that letter to see what it looks like in print. And if you do that, what are you going to lose? What are you going to give up? Well, you're not really going to be able to see paragraphs, or not even the sentence. You may not even see the words. You might, but you're focused on what you're going to see is what you're really interested in, is the font. Now, if you are an editor and your job is to read the material and see if it's using the proper English or Italian or whatever, then you don't care so much about the font. You care about a different resolution. You care about the ability to be able to read entire sentences, entire paragraphs. But if you are a layout artist and you're trying to lay out the page and decide what looks good on the page, you want to zoom out and look at the macro. You don't care so much about the fonts. You're not even concerned about what it says. You want to see the big picture. And that's what we mean by resolution. So when you're making measurements, I submit that you need to know what the resolution is of your measurement before you can make sense of it. Oops. Let's try it again. Don't crash on me now here. And this is something that we pulled from the archives when it says in his own words up here. This is Heyser's, in Heyser's own hand. We can't be precise in both time and frequency descriptions of the same event. The narrower the bandwidth, the more time it takes for a measurement. The smaller the time window of a switched measurement, the more smeared the equivalent frequency measurement becomes. If we clip out some part of one domain, we're going to lose sharpness in the other. And he says all the king's horses and all the king's advertising men can't put it all back together again, because it's the result of the way we define time and frequency. So let's see what this means, maybe in a more practical sense. So here's a measurement of a loudspeaker. And this is in 100 hertz of resolution. That means that the smallest squiggle, if you will, that you can resolve is 100 hertz wide. Any squiggle that's narrower than 100 hertz wide, you won't be able to see. It also means that it has a time resolution of 10 milliseconds. Now, that means that any reflection that's within 10 milliseconds of the direct sound is going to be included in this measurement. Another way you could think about that is a space dimension resolution. So any reflection from a that is within 3.44 meters of that 10-meter distance between the mic and the speaker, that will be included in the measurement. So that time and that space resolution are the same thing expressed two different ways. Okay, so this is a relatively high resolution in frequency, but very low resolution in time. I'll say that again. 100 hertz resolution means it's a high resolution in frequency and a low resolution in time. Here's a 500 hertz resolution image. Same loudspeaker, same setup, nothing changed except for we adjusted the controls on the TEF machine to a different resolution. Now we're using 500 hertz of frequency resolution. So that means we can't resolve any of these squiggles that are less than 500 hertz wide. And you see a lot of the little ones are gone. This is a 2 millisecond resolution measurement. So again, all the reflections within 2 milliseconds of the direct sound will be included. Now, obviously, there weren't that many. We don't see evidence of them. And a 0.69 meter space resolution. So things that are within essentially 0.7 meters of that 10-meter direct sound will be included. And finally, we see the other end, the other extreme, if you will, 1,000 hertz resolution. That means that we can't resolve any of the squiggles that are less than 1,000 hertz wide. It's a 1 millisecond time resolution and a 0.3 meter space resolution. So now we have a measurement that's very high in the time domain, very high resolution in the time domain, and very low resolution in the frequency domain. And in my experience, what we really wish is that we could have both, right? We wish we could measure exactly what the speaker does without any reflections and without having to worry about time. But you know what? You can't do that because these resolutions will always be the reciprocal of each other. So which one is right? And that goes back to our discussion earlier about it depends on which job you're doing. Okay, what Dick realized was that he had come up with a way of looking at least 3 dimensions of sound. Remember I said earlier that he believed that sound was n-dimensional and that we measure what we measure because we know how to. And that very possibly what we're measuring isn't even the right stuff to measure. Again, one of his passions was to figure out how do we measure the subjective? And how do we relate that to the objective? And he had all kinds of interesting ways of mapping one into the other, which is way beyond where we're going to go today. So here's the 3 or the 4 different measurements that we can make with the TEF, or displays anyway. The waterfall, or the 3D, looks at that TEF cube sort of in 3 dimensions. And you notice that you know, each one of these views gives up something, right? So if you look at the waterfall, you really are smearing both time and frequency. If you look at the FTC, you don't see amplitude. If you look at the ETC, an FTC, by the way, is frequency time curve. The frequency is along the x-axis and time is along the y-axis. Amplitude would be in a z-axis, if you will, coming out of the page towards you. The ETC is an energy time curve. This is energy as a function of time. This is an ETC of a room with you can see the direct sound, and we can see a very early reflection. I think these are 6 dB. That's about 9 dB down, and then we see reflections that come back and beginnings of a decay. And then, of course, our friend the EFC, most commonly known as frequency response. These are all part of what we call the TEF cube. Okay. I'm going to stop there in terms of the explanation of how the stuff works. I'm purposely not going to describe the ETC. That was something that came a little bit later. It's a fascinating process, but we don't have the time to go into it. And all this stuff is available if you want to read about it in the anthology, which I'll show you in a moment. Okay, I want to talk a little bit about the Heyser archives. Boy, I didn't put the year down, and I actually forget when this happened. It was around 2000, maybe 1999, when I contacted his widow, Amy, and got her permission to come out to California and pick up all of Dick's original test equipment, basically dismantle his lab, and get all of his papers. Now, one of the interesting things about the way Dick wrote his papers is he was maybe the last generation to write everything by hand. Word processing wasn't very popular and wasn't known really in his time. So instead of the way we do it now, where we write something and then we delete it and those deletions are gone forever, he wrote it all by hand and deleted it by simply crossing it out or circling it. And we can still see what he deleted, which is a remarkable insight into how his mind worked and things he wished he could say in some instances that he dared not say because of politics, quite frankly. So these links will be available to you. You can see the collection guide. You can see the materials guide, and then you can actually go to and download some of the unpublished works that we found when we went through his papers. And that's a fascinating read. We also, now Dick, we think of time delay spectrometry as something that we use for measuring loudspeakers. Dick had a much broader vision for time delay spectrometry, and we know that it was used in some of the early medical ultrasound imaging. Here's a picture of Dick staring into a slice of a brain that's suspended in some fluid, and he's using a form of time delay spectrometry to actually map to actually image that brain. And in the archives, we actually have some of the images as a result of these scans. So we know that it was applied to medical ultrasound. And I suspect even modern medical ultrasound probably uses some form of time delay spectrometry. He also applied it to mapping the seafloor. This was a towed array. Dick's there in the front. It was towed behind a ship and would actually make a TDS using time delay spectrometry, map the seabed or the ocean floor. And this was something that was used by the Navy. There were some all other things that he sold, that he gave to the Navy, which we can't really talk about too much, but he had come up with some systems for from in the Department of Defense for looking at defense systems for submarines. So a few glimpses from the archives. So, in his own words, you may have thought, and indeed may have been misled into thinking, that TDS is a testing method limited to a linear frequency sweep and a tracking filter. Not so. TDS is much more, and the present TDS instruments, as good as they are, represent only the very first steps into a newer realm of analysis and test. Here's one of my favorites. The laws of math and physics are the same for TDS as for any other fine systems which are capable of displaying restricted bandwidth interval measurements. There is, however, one overriding consideration which is glossed over by those who play with frequenciness and timeness and things involving the Fourier transform. In all caps, the Fourier transform only works for linear systems, double exclamation point. This was one thing he was passionate about. And he said, and we have the documents that show that what he had discovered, that the Fourier transform was actually what he called degenerate, not in the sense that it's a bad thing, but in the mathematics sense, transform of a bigger transform, which he called the Heyser transform. But this slide has a second part. If you've got a nonlinear system, and who in this business can guarantee linearity, then you get yourself into big trouble by blindly using the Fourier transform and things related to it. Now, I'm not going to make any judgments. You guys using FFTs, I'm just telling you what Dick said. He was passionate about the fact that audio is multi-dimensioned. And he was trying to convince people to start looking at the subjective attributes of audio. And he suggested different coordinates of measure and ways to map them from one to another. And it's really intense and interesting stuff. Couple more slides. Oh, somehow my slide about the anthology got dropped here. I'm not sure what happened to it, but there is the AES published an anthology of his collected published works, and that is available from the Audio Engineering Society. It's the only anthology published of an individual's work, and it's tough reading, but it's good reading. It also includes a number of articles that were written for Audio Magazine, which Dick really dumbed down for the use of his readers. So I strongly suggest that if you get yourself a copy of this anthology, you start by reading the articles designed for Audio Magazine. It'll help you get a sense of what he was trying to say. And then you can, pour yourself a shot of lovely Irish whiskey and dive into the meat and potatoes of his technical papers. Now, one of the things that Dick loved to say is that sound is what happens when air gets pushed. That was one of his favorite quotes. And I was delighted to find this little scrap in the archives, because this apparently is the first time that thought, sound is what happens when air gets pushed, occurred to him. And we see his thought process captured for us right here. So he says, sound is what and he starts to write out result, and he crosses that out. So sound is what happens when I don't want to say that, cross that out, when air gets pushed. Pushing on air, whether by a loudspeaker cone or, and then he tries to say human vocal cords, and he crosses that out, and he says, or any other means, does work. So what he wound up with was sound is what happens when air gets pushed. Pushing on air, whether by a loudspeaker cone or by any other means, does work. And his point is that when a loudspeaker's cone moves, it pushes the air, and pushing air is work. And that's why it requires power to do that. And this launches into a whole paper on energy, which is a fascinating read. Now, the final slide I want to show you, it was actually taken from a screenshot, and I have the original of this somewhere, but I couldn't locate it. He said, as a warning, the days of the blind giant are coming up fast. What Dick was talking about was the digital age. He died just as the digital age was starting to take shape. And I think he looked ahead and said, man, we've got to be careful here. Because what the fast computers are going to be able to do is going to make it look like we can violate a lot of laws of physics when we can't. So with that, I leave you, and we can take some questions. We can see if maybe Tom is able to get the microphone working and wants to jump in and say anything.
So thanks, Doug. That was brilliant. I don't think I've ever seen a clearer explanation of how TDS works.
Well, thank you. Thank you very much.
We don't have any questions yet, but I think just with the time of day that we don't have many people watching, and we'll probably have a lot of people who look at it afterwards.
Got it.
I have a question though.
You do? Okay.
I probably have a lot of questions, but I'll limit it. Okay. What's very common at the moment, due to the speed of use, is to optimize a sound system with multiple time windows, or there's several different names for the same thing, using just phase and frequency. Now the windowing is all kind of hidden, and generally you have maybe two options. You can have one where it has a closer window and one with a further out window. Are there any obvious limitations to that approach that you can see?
Well, I think the way I'd like to respond to that is that, remember, the time delay spectrometry is not a real-time measurement, right? It's a two-port device. It has an output, which is an analytic signal that it creates. So in some sense, it knows, if you will, what's going out. And it has an input that's looking for that specific output, if you will. And so it is not real time. It takes time for that process to occur. And so I think it depends on what you're doing. If you're setting up a sound system for a band and the show has to go on at 8:30 and you've only got an hour, please don't bring a TEF. That's a waste of time, because it'll take you too much time. Yeah, you're going to get the right answer eventually, but it's going to take you a long time getting there. In that instance, you're much better using something that is a real-time analyzer that's making its measurements instantaneously. And, you know, there's many of them out there that work and will get the job done. But I think what Heyser's saying is that every time you use the FFT, you're assuming that the system is linear, and it isn't. And so there's going to be some error. There's going to be some error. And the trade-offs are going to be there, whether you can see them or not. Now, that may not be serious enough to care about when you're setting up a PA system for a band. But if you are a loudspeaker designer, or if you are trying to figure out what is wrong with this loudspeaker, and you're not at a show, and you're back at the shop, and you want to try to figure this out, that's when a machine like TEF really shines. That's when there really is no other way to do it. Now, I think Tom is still probably having trouble with his microphone. But I'll just say that, you know, Tom is a dear friend of mine. I worked for Danley for a number of years, and Tom and I worked very closely together. And, you know, he uses a number of different measurement tools to measure the loudspeakers. But when he's designing the system, the loudspeaker, and making measurements to see how they're working and to see if his ideas are moving in the right direction, he always relies on time delay spectrometry because it's the best system out there.
Absolutely.
And Tom, if you disagree with me, just write me a nasty chat here. So I don't know if that answers your question, Abe.
I think it did, yeah. And we have a question from YouTube. This one is from Kyle in Manchester.
Hi, Kyle.
Is the wavelet transform not essentially the same approach as TDS, but fixed in post? The increased flexibility of capturing the raw response rather than having to make multiple sweeps is a big help.
Yeah, I don't know enough about it to answer that with a lot of confidence, but I suspect that it is similar. I suspect that if Heyser had lived into the age of the giant he talks about, that we would see a lot more sophisticated ways of doing time delay spectrometry that would be much faster and much easier to implement. It wouldn't take as much time. So, I mean, yeah, he may be right, but I'm not qualified to answer that.
So I have another question that's probably most obvious question. And that is, TDS seems like it became not popular because it depended on hardware. So you were, you know, if you weren't willing to pay for the hardware, you didn't get to use TDS. But you can get software now that has TDS. So like Isara, I don't know, or Isra, I'm not sure how you pronounce that. Is there, or are there things that you feel are definitely being missed out on by people who haven't taken the time to look at TDS? Like in the current context, where there are things like wavelets and MLS, are there benefits that you still see in using TDS?
Yeah, MLS doesn't do what the TEF will do. It doesn't do what TDS will do. It especially in the low end, it can't. It's not. It's a good form of measurement. It works. And in the software that comes with the TEF 25, you can do MLS. And it gives you a great opportunity to make measurements of the same device using MLS and using TDS. And you'll see there's a difference, a significant difference. There may be times where the MLS is useful. Off the top of my head, I can't think of one where I would say, oh, I'm not going to use TDS here, I'm going to go to MLS, because it doesn't actually give you the noise immunity that the TEF would, that the TDS would. As far as other systems, yeah, I mean, my hope, my dream for doing this this presentation is that somebody out there who is a bright, mathematically inclined person who's looking for a research project, that you'll go to the archives, you'll look through his stuff, you'll read his material, read the stuff that isn't published, read the stuff that's in the archives, if you will, and come up with a newer and better and faster way of doing time delay spectrometry and bring it back to the world, and do it in software. Certainly computers are fast enough nowadays to do that. There's no reason it can't be done. But I hope that, I mean, I made a promise to Amy Heyser that I would do everything I can to prevent his name from being forgotten, and to prevent the stuff he invented from being forgotten. So for me, this is a way of continuing to fulfill that promise. I still think it's a valid tool. I still use it. I know that I'm, a dying breed, but I don't know if that answers your question.
I think it does, yeah. Do you have any questions, Fidel?
There is another question on YouTube, Abe.
Okay, sorry, I didn't see it. The ISRA version of TDS isn't strictly the same approach as Goldline TEF, by the way. It's applying a fixed low-pass filter to a captured impulse response as post-processing, similar to time windowing, but not the same. I obviously didn't read that before speaking it out, because that's a statement, not a question. But that is interesting, Kyle. Thanks.
I'm sorry. Something just popped up here from Tom. He can't get his mic to work. He says, yeah, MLS has much less noise rejection. And he says, explain how the bandpass filter part is like an AM radio. That's something that Tom can do that I'm not even going to go there. It's all about heterodyning and so forth. Let's see. And then he said in one of his papers, he talked about the log sweep. And I think he was anticipating that was going to be a good way to do this. So these are some comments from Tom. And I'm sorry, could you repeat that question that came in? I got distracted by Tom's text here.
It's okay. It was yeah, no, it was Kyle was mentioning how TDS is implemented in ISRA. It was a comment on how it's not the same approach as in TEF. It applies a fixed low pass filter to a captured impulse response as post processing, similar to time windowing, but not the same. And there is a paper by Wolfgang Anert about implementing the approach, which in the AES archive, that's supposed to be interesting.
Yeah. And in fact, in a beta version of software that runs on the TEF 25, there was the ability to do a similar thing where you could capture the impulse response and then post-process it into TDS measurements that way.
Okay. One of the things in our chat before the webinar that she said that I found interesting and hadn't really thought much about was how with most measurement systems the phase is relative as opposed to absolute. Do you think that there is, or how important do you think that actually is, that measuring?
Well, it's important depending on what you're doing. So one of the things that we've discovered over the years, as those of us who, were fortunate enough to meet Dick and to learn about TDS and then watch it grow throughout the years, winding up with the the TEF25 and then some of these newer software implementations, is how the different machines handled phase. So if you were to build an analog 4-pole filter, you must have 360 degrees of phase shift. That's the rules in the analog world. So if you measure that with a TEF10 or TEF12, you will always see 360 degrees of phase shift. Always. The phase detector was never fooled. No matter how you did it, it would always show you the correct answer. If you did that with a TEF20, most of the time, it would show you the correct answer. Under some conditions, the 25 will show you an error. The phase detector wasn't quite as good. I don't know about some of these other systems. So I would suggest, but again, if you're measuring a sound system before a show, who cares? I'm not sure what phase means in that situation, but maybe that's because I'm not smart enough. But if you're designing this loudspeaker and you're working on it and you're trying to get an optimal frequency response, or you're working on the crossovers, then phase really does matter. And it really does matter if your phase detector is giving you the false results. If it's not showing you the difference between 0 phase and 360 degree phase. Yeah, Tom just said the TEF and 12 did a quadrature phase detection and later ones were one-sided, and that's correct. So again, if you're designing the speaker and or the crossover, then yeah, phase matters and it has to be right. If you're not, then who cares? But again, try it on your machine. Try smart. Build a 4-pole analog filter and connect it to smart and see what happens.
So one of my observations is that while I wait for another question, one of my observations is that there seems to be wider use of measurement than ever before, and the tools for simulation and for measurement seem to be pretty commonplace. Most people know what a rate calc is, and or whatever the simulation software is of the manufacturer that they use. But it also seems like the majority of what people look at is just magnitude and direct sound and magnitude, maybe the phase trace as well. And what I've often noticed is that if you use these tools and you only look at the direct sound, magnitude, and phase, you don't necessarily know the reasons why, if you're going to use a line array, hanging it a bit lower and keeping it straighter is going to give you a different result, but you might not see a different result in your measurement or your simulation. Right. If you use point source speakers, like if you use Danley speakers, synergy horns, most of the benefits of a synergy horn can't actually be seen if you only look at magnitude and phase. So, we have all these tools, even most of our acoustic modeling software, it doesn't actually show us that much about, what happens in distortion or whatever.
Well, I mean, you speak of distortion. I mean, Heyser wrote a whole paper on measuring distortion. So again, the anthology is full of really important information on that. I want to try to respond to your comment by taking us back to Dick Heyser. His passion was to figure out, how do we map? How do we measure the subjective? How do we figure out what's making the speaker sound the way it does in a subjective world? And what bothers me is that in the years since Heyser died, that conversation has disappeared, as far as I can tell. Nobody's asking these questions anymore. People are coming up with fancy ways of measuring the same old stuff over and over and over and over again. But no one is asking the question, how do we map this? How do we figure out what is happening in the subjective sense? And how do we measure that using what tools? No one talks about it. And that's the tragedy, I think, of losing Heyser too soon. Yeah, and Tom just popped up with a chat. Dick's thing was trying to tie measurements to what we hear.
Yeah, that seems like it should be obvious and important.
Well, it should be obvious, but I don't see people talking about
it. It'd be great to get your perspectives on what it was like being, actually experiencing Heyser workshops and being at the forefront of the technology, seeing the new tools that were becoming available, like how to measure STI, things like that. What was it like at the time?
Well, I think you can say a lot about the boomers, yes, boomer. But people my age lived through a remarkable era. I mean, I remember as a kid changing vacuum tubes in my, our kitchen radio, taking the tubes down to the corner drugstore and plugging in a tube tester, and all the way up through transistors and chips, and then these massive integrated circuits that had billions of things on them and so forth, into the digital age. And so now when we talk about audio, digital is the normative, whereas for my generation, we still wrapping our heads around, oh yeah, that's right, it's digital now. Whereas for your generation, it's always been digital. What it's hard to explain what analog was. Indeed, a lot of people can't explain what analog means. It's a word that's funny. Analog, what? So for me, I was in my 20s when I first went to a SynodCon workshop. And this was all brand new stuff. And it was like, trying to drink from a fire hose. There was so much stuff that it took a long time to process it. And those of us of that generation were so fortunate. I mean, where else would we have met people like Dick Heyser? I mean, how would my life ever intersect with his? He's a senior scientist at Jet Propulsion Labs, designing, satellites and imaging systems, and designing stuff for medical ultrasound research and stuff for the Navy and stuff for who knows what. And I'm just this kid. How would I have possibly met him? How would I have possibly met people like Doc Bertonis, who became a real mentor for me, and so many others, and Don Davis. Goodness, I mean, here's a guy that changed the world, literally. And so those were really heady days, and to get to meet Dick and talk with him and realize that he was a lonely guy, because not many people could understand him. And he wished that people could understand him. But, in the conversations I had with him, I knew he was dumbing it down. He was very kind and gentle in that way. He says, oh, okay, I'm not going to hit you with the heavy calculus because, but he loved to say that nature doesn't solve equations. So he understood calculus and its need and the higher math, but he realized that what really mattered was the way you look at things and how things sound and how we could somehow advance the technology to get to the point where we could begin to analyze that in a meaningful way. So yeah, it was wonderful. And I'm sure that every generation thinks that, and for every generation, your lives are full and exciting, and you get to witness new things getting developed. And we don't know what's coming, so who knows? But anyway, I don't know if that captures a little bit of what you're looking for.
Does, yeah. I appreciate that. Thanks. I have another couple of comments. Have we had any joy getting Tom's audio working, or is it still?
No, I
got VU, but
I don't think so.
I think I heard something there, but it was just very quiet.
oh, okay. Can you hear anything now?
Yeah, we're hearing you. Turn it up.
Oh, okay. I'm about clipping, so
That's good. That's good right
it's
there.
a measurement mic, so this is what I really sound like.
If you're not redlining, you're not headlining, Tom.
Okay. All right. I'm sorry. What was the question?
So Tom, it's kind of similar, but is there any chance you could talk a bit about your experience with Heyser workshops, things like that, using, why are you still using TDS, all those questions?
Okay. Well, let's see. My boss at Intersonics saw an article about SynodCon and said, boy, that sounds pretty cool. And maybe a month later, he bit the bullet and brought a TEF machine. And that's when I started going to SynodCon. Actually, it was a comment that Don Davis made that about 10 years later led to the synergy horns that we're making now. It was really quite an experience going to the first few of those. It was, I think I probably said 4 or 5 words during the whole time. There was one event. Well, it was an informal thing. Don and Carolyn were walking by our booth at a trade show and asked if I wanted to walk with them. So I did, a chance to get away. And that ended up being a dinner. And Gene Petronas and Dick Heyser and a bunch of other people were there. And Don tossed me a softball question that I answered, but I think that's the only thing I said. It was really intimidating, actually. Let's see, as far as the TEF, it is like what Doug said. It's got much better noise immunity. If you do the log sweep, the convolve the log sweep approach and average some of those, you can get pretty close to the TEF. But the TEF does it in one shot, and it's straightforward and simple, and I understand it. I like it a lot.
We have another couple of comments in the chat. Kyle said that is the CTA 2034 standard championed by Floyd and Olive an attempt to continue Heyser's approach of using measurement to quantify objective perception? This assumes that you know that standard. Likewise for clarity metrics, C80, etc.
I'm not sure, to tell you the truth. I haven't followed that closely. The measurement that does seem to hold some, let's say it's some kind of an indicator on a property that doesn't show up in other measurements, is the modulation transfer function. Like in ARTA, for example, you can do that. There's no quantitative result. It just gives you a curve, but that does seem to pick up stuff that are missed, I guess. Excuse me.
And Charlie Hughes actually commented on that also in the chat. He said that he thinks CTA 2034 is a limited attempt at that.
I got you.
Yeah. And there's a joke in the comments about, was your tracking filter bandwidth too narrow, Tom?
No, I think my gain wasn't up high enough. No, I had to switch to a different microphone, and I just turned it up so I saw the level indicator, but it wasn't high enough.
Okay.
So we know when Tom was, but not where, or where Tom
Yeah.
was, but not when.
Okay, Fidel, have you any questions?
No, for me it's all. Thanks to all. I want to thanks also Ivan Beaver, Charlie Hughes, and Pat Brown for the suggestions that they do to me, and I thanks there a lot. Thanks to all you guys. Thanks to Doug Jones. Thanks to Tom Danley for his presence and the testimony, and thanks to all for watching. Thanks, Abe, also for your work.
No problem.
Many thanks. Okay.
Yes, Abe, thank you so much.
Okay, I think is all. Ok.
Thank you.
Ciao, grazie.
Ciao.
Per gli
Ciao.
amici italiani ricordo che nei prossimi appuntamenti inviterò, avrò ospiti, amici, utenti italiani del TEF, probabilmente tra i primi utilizzatori italiani del TEF. Prossimamente nei giorni 31 e 30. Marcello Croce nel webinar del 30 gennaio e Fabrizio Calabrese nel webinar del 31. Thanks to all, thanks to watching. See you. Ciao.